Assalamu alaikum. Today on 7th January 2021, I'm starting lecture number 2 for week number 14, and the topics that we will cover in this lecture is the starting principle of synchronous generators, synchronous motors, uh, equivalent model of synchronous motors, Phasor diagrams associated with it, and finally uh, the constant speed characteristic of synchronous motor. So these are the topics that we will study today. So starting from a brief introduction of synchronous motors. Synchronous motors are synchronous machines. If you recall chapter number 4, where we had a short introduction of AC machines. So I told you that there are two major types of AC machines. One is the synchronous machine and the other is induction machine. In synchronous machines, field current is provided by a separate DC source, while in induction machine, field current is provided by means of induction. So synchronous motors are synchronous machines. Here we provide field current with the help of a DC source. Uh, as generator, synchronous machines are widely used in all electricity producing plants, all IPPs, hydroelectric power plants, fossil fuel power plants. But as a motor, uh, synchronous motor is not a very famous type of motor. Actually, long time ago, when parasitic capacitors were not there, these machines, that is synchronous motors, were used to provide power factor correction in their locked rotor condition, where they are using with they are being used with a leading power factor to provide power factor correction for the system, for electrical power systems. But as parasitic capacitors were introduced in electrical power systems, so they were quite inexpensive as compared to synchronous motors. So due to this reason, uh, the use of synchronous motors become uh, quite low after the introduction of parasitic capacitors. Still, old plants where uh, good synchronous machines were installed, they are still doing their work because the investor has invested the money now and the machine is working good. So they are not uh, bothered that why should we replace these motors with the parasitic capacitors while we have invested uh, the required investment quite earlier. So they are using synchronous motors. So synchronous motors run at constant speed. The name synchronous is due to the reason that they run at constant speed. Their mechanical speed is basically locked with the electrical frequency, as we studied in chapter 4, that the mechanical speed of rotation Nm could be given as 120 time frequency whole divided by number of poles P. So suppose we have a 4-pole synchronous motor, so its speed would be 120 multiplied by 50 whole divided by 4, that is 6000 divided by 4, that is 1500 rpm. Later on we can convert this speed into radian per second by multiplying the revolution per minute with 2 pi by 60. So synchronous machine run at constant speed, so they may be used in the applications where we need a constant uh, load to be taken by a motor. Unfortunately, in our industry and in most of the applications that we use in daily life, We seldom require motors that work at constant speed. Most of the time, we need to operate the motors in a variable speed way. For example, uh, if you take the example of elevator or lift, what happens that when you get into the lift and you press the start button, it starts slowly, then it speeds up, and when you are near to your destination, it becomes slow again. So in a simple application of lift even, we need variable speed. So due to this reason, synchronous machines are not very famous as motors. They are not very, you know, user friendly because they run at a constant speed. And in our most of applications, we need variable speed. In industry, three-phase induction motors are the most widely used motors. Still, the author has given an entire chapter to this motor. In my opinion, it's not worthy of it. But still, since they had given an entire chapter, so we will cover some of the important parameters uh, and features of this motor. So starting with the starting principle of synchronous motor, what happens that we provide three-phase set of voltages that are equal in magnitude, differed by 120-degree phase angle, to the three terminals of synchronous motor stator. So these three-phase set of voltages produce a rotational magnetic field. Now we provide the field winding or the rotor winding with a separate DC source. So this DC source provides a stationary, a uniform magnetic field at the rotor. So the stator's magnetic field BS is rotating. It's in nature, is in its nature, and stator's magnetic field BS rotates about the rotor, while the rotor's magnetic field BR is due to a DC power supply, so it is stationary, it is constant, it's uniform. But what happens that the rotor's magnetic field tries to catch up with the stator's magnetic field, and in an effort to be aligned with the stator's rotational magnetic field, the rotor's magnetic field, and hence the rotor starts rotating. So this is the starting principle of a synchronous motor, that we provide three-phase set of voltages to the stator's winding. These three-phase set of voltages that are equal in magnitude, differed by ideal 120 degrees apart. These voltages produce a rotational magnetic field Bs. We provide the rotor winding with a fixed DC supply, so it produces a fixed magnetic field Br. Now the rotor's magnetic field Br tries to catch up or to be aligned with the stator's magnetic field, and in this effort, the rotor and its magnetic field start rotating, and hence we say that three-phase synchronous motor is a self-starting motor. We do not use any special technique to start this motor because it is self-starting. So this is how we start the synchronous motor. Now coming to the next topic, the equivalent circuit or equivalent model of a synchronous motor. As in the last chapter, we studied the synchronous generator's equivalent model. And if you recall in chapter number 1, I stated that the same machine can act both as a motor or as a
Excuse me, sir.
generator. G.
Sir,
G,
what do we mean by self-starting?
yeah, self-starting means that we do not require a special circuitry to make the machine rotate. For example, in our home appliances, we do have a single-phase induction motor for the provision of water in our home. Uh, so what we do, that we press the button and the motor starts rotating. So in this way, This is also a self-starting motor, but this is not the case. Why? Because in our home, the motor that is being installed is a single phase induction motor. When we switch on the button, it starts rotating due to a special circuitry installed in it. What is that special circuitry? Actually, a single phase motor can never rotate until or unless a special starting scheme is provided to it. For example, in our motors, for example, the motor that is being installed in your ceiling fan, you can observe that there is a small capacitor installed nearby the motor. So when we switch on the motor, what happens that this capacitor provides a phase difference between the current flowing in the motor winding and the current that is being flowing through the capacitor. So due to these two phases, there is a phase difference is created, and now this single phase machine basically starts rotating as a two-phase machine. If we remove the capacitor of the ceiling fan and then we start the button, then we push the start button, the motor will never rotate, the fan will never run. Why? Because this capacitor is the special starting circuit for this motor. Without this capacitor, the motor can't rotate. So all single phase motors need a special starting technique, while three-phase induction or synchronous motors do not require any special starting technique. What are the different names of starting techniques? For example, single phase induction motor. Single phase, number two, single phase capacitor start motor. Number three, single phase repulsion motor that starts on the principle of repulsion. Number four, shaded pole motor that starts with the help of its shaded poles. So there are a lot of techniques that convert a single phase motor into a two phase motor, and hence the motor gets started. But three phase motors, they start automatically due to the rotational magnetic field produced by their stator's winding. So since synchronous machine also have uh, the rotational magnetic field of stator's three-phase winding, so therefore it is not uh, started by a special starting technique, rather it is a self-started motor. Hope you got my point that single phase machines are not self-started. Why they are not self-started? Because if you will remove the special starting circuitry from them, the special starting circuitry that is being attached to them, they will not start, they will not run. I gave you the example of ceiling fan. You have a capacitor installed over there. If you remove the capacitor and just short circuit the winding there, and then you press the button on, the machine will never start. It will never rotate. Why? Because this capacitor was responsible to provide the initial torque, was responsible to start the machine as a two-phase machine. Later on, the capacitor may be removed from the circuitry. For example, you start the button, capacitor is installed, it gave the single phase machine an initial torque, the machine started rotating. Now if you can remove the capacitor, it will keep rotating. But right in the initial time t equals to 0 plus instant, we need that capacitor to be installed there. Okay, so this is the case. Now coming back to our next topic, the equivalent model of the transformer. So I was saying that in chapter 1 I stated that the same machine can act both as a motor or as a generator. It is the direction of current flow that determines whether the machine is acting as a motor or as a generator, or it is the direction of power flow that determines whether the machine is acting as a motor or as a generator. So without giving uh, any further detail, what happened that they had drawn the model of synchronous motor directly. Why? Because in the previous chapter, in the last chapter, that is synchronous generators, we have studied this model. If you recall, the left hand side was the field circuit, where VF was the DC power supply, IF is the DC field current flowing in the field circuit, IF sorry, and RF and LF are the field resistance and the field inductance respectively. So what is happening there? What is happening there? That on the left hand side we have the field circuit, and on the right hand side we have the armature circuit. Now if you notice that this time the armature current has a reverse direction. Previously in synchronous generators, armature current was flowing from the internally generated voltage EA towards the output phase voltage V5. But this time IA, that is the armature current, is flowing from the output phase voltage towards the internally generated voltage. So in short, we can say that in synchronous motors, the direction of current flow has reversed. And why is it so? Because we are providing the machine with three-phase power supply. They have not written it here, but I am telling you that on the right hand side, what we have basically three-phase supply. Like in a single-phase motor, we provide the motor with a single-phase supply. So a three-phase synchronous motor has a three-phase supply towards the right-hand side. Now, when we connect these three phases to the three terminals of the stator, obviously, current will flow from the Vabda sides towards the motor side. As when we start the motor installed in our home, what we do, we press the button and the current starts from our hand side towards the motor side. The current starts flowing from our hands towards the motor. So this is the case that when we connect the synchronous motor from a three-phase supply, so what happens that from those three phases, currents start flowing towards the three terminals EA1, EA2 and EA3. And obviously due to these three-phase voltages, a rotational magnetic field is produced and hence the motor starts rotating. So the only difference between this circuit and the previous circuit that was explained in chapter 5 is the direction of current flow. And what is the only consequence of this change? The only consequence of this change is that the machine starts working as motor, and there is a change in KVL as well. If you recall in chapter 5, we used to write V5 equals to EA minus XSIA minus RAIA. But here, when the machine is acting as a motor, we are writing EA plus XSIA plus RAIA. Why these two terms are now being added? Because the direction of current is not IA, it's now minus IA. And due to this minus IA, the minus of minus excess IA becomes positive. And hence, rather than subtracting the two voltage drops from EA, we add the two voltage drops into EA to get the output phase voltage. So this is a difference that will come in the derivation or the equation algebraically. Now, if you recall, I asked one question in our midterm exam that draw the exact equivalent model of a single phase transformer and explain each term. In a similar way, if I ask draw the equivalent model of a synchronous motor and explain each term, then you must be capable enough to differentiate between the model of a synchronous motor or the model of a synchronous generator. Why I'm saying this? Because often what happens that I ask to draw the model for a synchronous motor and they draw the model for a synchronous generator, ignoring the fact that in case of synchronous motor, IA must flow from V5 towards EA. There must be a three-phase supply towards the right-hand side. So if you will not mention these things, so a marks detection can be uh, obviously done for this mistake. Okay. So this was all about the equivalent model of synchronous motor. Now coming to the second last topic of today's lecture, and this is the phasor diagrams of asynchronous motors or synchronous generators as well, because here they have discussed both phasor diagrams for synchronous motor and the phasor diagrams for synchronous generators. And what is the topic here? Actually, the author intends to give you a simple justification or simple rule to identify that whether the phasor diagram drawn is for a synchronous generator or it is drawn for a synchronous motor. So he has told three different rules. I tell you all the rules one by one. First of all, for figure 6.3 part A, he says that if the internally generated voltage in a phasor diagram is ahead of the output phase voltage V5, then it is confirmed that the phasor diagram belongs to a synchronous generator. क्या उसने कहा कि अगर एक फेजर डायग्राम में इंटरनली जनरेटेड वोल्टेज EA आउटपुट फेज वोल्टेज V5 से आगे हो, तो ये कंफर्म है कि ये जो डायग्राम है वो एक सिंक्रोनस जनरेटर की फेजर डायग्राम है। यानी ऑथर चाहता क्या है कि आप फेजर डायग्राम देखते ही समझ जाएं कि ये सिंक्रोनस जनरेटर की है या मोटर की है। तो उसका उसने एक रूल बता दिया कि इसका बगैर कैलकुलेशन के भी एक आसान सा रूल है कि अगर EA V5 से आगे होगा तो इसका मतलब है कि फेजर डायग्राम सिंक्रोनस जनरेटर की है। पहला रूल उसने ये बताया, ठीक है जी। आप देख सकते हैं कि here V5 is at positive x-axis, so its angle is 0, and EA is somewhat ahead of V5, or the angle between V5 and EA is the torque angle delta. So this torque angle is approximately 30 degrees. So we can say that internally generated voltage EA is ahead of V5. So the phasor diagram belongs to a synchronous generator. In a similar way, this can be predicted using the corresponding magnetic fields diagram. In figure 6.3b, what we can say that if the rotor's magnetic field is ahead of the net magnetic field, then the machine is acting as a generator. And again, clearly B net is along the positive x-axis, BR is at an angle delta from B net, and it is approximately 30 degrees ahead of B net. So we can say that the machine is acting as a generator. दो बातें हो गई। तीसरी बात, ऑथर ने बताई है और है बहुत मुश्किल है, लेकिन मेरा असूल ये है कि हर बात बता देनी चाहिए। बात होता ही है कि हमें एक चीज मुश्किल लग रही होती है, स्टूडेंट को आसान लग रही होती है। तो तीसरी बात उसने ये बताई कि देखिए अगर आप फिगर 6.3 बी में, तो डब्ल्यू सिंक्रोनस की जो डायरेक्शन है कि मशीन किस डायरेक्शन में रोटेट कर रही है, वो है काउंटर क्लॉकवाइज डायरेक्शन। और अगर आप टॉर्क का फॉर्मूला यूज करते हुए और बी आर क्रॉस बी नेट का जो फॉर्मूला है वो यूज करते हुए डायरेक्शन मालूम करेंगे इंड्यूस टॉर्क की, तो वो क्लॉकवाइज निकलेगी। तो उसने ये कहा कि इन अ सिंक्रोनस जनरेटर द इंड्यूस्ड टॉर्क इज ऑलवेज इंड्यूस्ड अपोजिट टू द डायरेक्शन ऑफ रोटेशन। तो ये तीसरी निशानी उसने बता दी, लेकिन मेरे नजदीक ये बड़ी मुश्किल निशानी बताई है, बच्चों को समझ नहीं आ सकती, लेकिन चले उसने बताई तो मैंने भी आपको बता दी। अब नीचे वाली जो दो फिगर्स हैं ये सिंक्रोनस मोटर्स के लिए। तो ऑब्वियसली जाहिर है जो चीज सिंक्रोनस जनरेटर के उलट होगी वो सिंक्रोनस मोटर के लिए होगी। तो हम कह सकते हैं, बड़ी आसानी से नोटिस कर सकते हैं कि इन फिगर 6.4a द इंटरनली जनरेटेड वोल्टेज EA is behind the output phase voltage V5. So obviously it is a synchronous motor, because in synchronous generator EA must be ahead of V5. So here EA is behind V5, so it is a synchronous motor. Similarly, in figure 6.4b, since BR is behind B net, so it is synchronous motor. Why? Because in synchronous generators BR is ahead of B net. And in the third case, in figure 6.4b, the actual rotation of machine is counterclockwise direction, in counterclockwise direction as depicted by W synchronous. W synchronous को देखें तो counterclockwise का symbol बना हुआ। Now if we calculate the direction of torque of that is the direction of induced torque, so it is also counterclockwise. So since induced torque and actual torque both are in counterclockwise direction, in the same direction, so machine is acting as a motor. तो ये बातें हो गई फेजर डायग्राम्स के बारे में। अब आ गई लास्ट टॉपिक आज का, और लास्ट टॉपिक है the steady state or constant speed of a synchronous motor. Right from chapter 5, we kept saying that synchronous machine run at a constant speed. They work at a uniform speed. Their speed does not change. लेकिन आपने लैब में देखा होगा कि जिस भी मोटर पे आपने लोड अप्लाई किया उसकी स्पीड तो कम ही हुई है, तो फिर इसकी स्पीड कम क्यों नहीं होती? सवाल है ना कि whenever we apply load by means of an electrodynamometer in our lab, we used to notice that the speed of the rotor is decreased. Then why in case of synchronous motor it does not have a speed reduction? I will answer this question sometime later. First of all, let us uh, follow or examine the speed torque graph of a synchronous motor. So this is the speed torque graph of a synchronous motor represented in figure 6.5, where what is happening that the speed of synchronous motor Nm is constantly at this line, despite of the torque applied at the shaft of the motor to be increased from 0 to the pull out torque. This is the pull out torque, and this is the value of the rated torque. Why these two values are important? Number one, the machine is designed to operate at its rated torque. To be operated at its rated torque. Suppose the rated torque is 50 Newton meter. So the machine is designed to operate at 50 Newton meter, and it will run at a constant speed at 50 Newton meter. Now, to what extent it will operate at constant speed? Thrice of the rated torque. And thrice of the rated torque is known as the pull-out torque. So machine is designed to run at a constant speed, suppose 1500 RPM. From its rated torque to thrice of its rated torque. यानी इतनी फ्लेक्सिबल जरूर होती है सिंक्रोनस मोटर कि अगर वो 50 न्यूटन मीटर का काम उसने करना है अपनी शाफ्ट पर, तो वो 50 मल्टीप्लाई बाय 3 150 न्यूटन मीटर तक भी वो कांस्टेंट स्पीड पे ही रहती है। लेकिन अब मैं ये कह दूं जी सिंक्रोनस मोटर कांस्टेंट स्पीड पे काम करती है और एक छोटी सी सिंक्रोनस मोटर के सामने एक हमारे स्टूडेंट ट्रक लगा दें और कहें भाई ये तो कांस्टेंट स्पीड पे काम करती है, चलती रहेगी और ट्रक भी चलता रहेगा, और वो बनी बेचारी वो शायद किसी खिलौना साइकिल के लिए हो, आपने उसके साथ लगा दिया ट्रक और आप कहा कि सर ने जो कहा था कि ये कांस्टेंट स्पीड पे चलेगी तो अब ये कांस्टेंट पे ही चलेगी। तो देखिए ऐसा नहीं होता। ऑब्वियसली जो डिजाइनर होता है उसे पता होता है कि मैंने जो मशीन बनाई है ये किस चीज के लिए बनाई है। तो ये जो हम बात करते हैं सिंक्रोनस मोटर की कांस्टेंट स्पीड पर चलने की, वो अपने रेटेड लोड के लिए भी कांस्टेंट स्पीड पर चलती है, और इन केस किसी माल फंक्शनिंग की वजह से या कभी कभार कोई लोड बढ़ जाता है तो इवन वो इतनी फ्लेक्सिबल तो होती है कि अपने रेटेड लोड से थ्राइस लोड तक भी वो कांस्टेंट स्पीड पर चलेगी। लेकिन अगर आप उसके सामने वो साइकिल के लिए बनी थी और आपने ट्रक लगा दिया है, तो ये तो एक ह्यूमन साइकोलॉजी भी है ना कि छोटी सी मोटर ट्रक को कैसे चलाएगी। तो होगा क्या कि इस सिचुएशन में अगर उस पर पुल आउट टॉर्क से भी ज्यादा टॉर्क अप्लाई किया जाएगा, बहुत बड़ा लोड उस पर अप्लाई कर दिया जाएगा, सो एट दैट मोमेंट सिंक्रोनस मोटर विल लूज इट्स synchronism. This situation will be called slipping poles situation. If we apply a load that is beyond the pull out load or pull out torque of a synchronous motor, then the machine will lose its synchronism. It will be a slipping poles situation where what happens that the machine will start vibrating. It starts doing to and fro motion. It starts doing oscillatory motion, and due to excessive oscillations it will get damaged. वो खत्म हो जाएगी। जब मैं लैब में खुद एक्सपेरिमेंट करवाता था तो मैं सिंक्रोनस मोटर पे थोड़ा सा पुल आउट टॉर्क के करीब टॉर्क थोड़ी सी देर के लिए करवाता था ताकि बच्चों को पता चले कि ये बात हवा में नहीं है, प्रैक्टिकली वो वाइब्रेशन शुरू कर देती है, शोर मचना शुरू हो जाता है लैब में। लेकिन ऑब्वियसली क्योंकि हमने मशीन डैमेज भी नहीं करनी होती थी तो हम फौरन से उसको वापस ले आते थे। लेकिन ये हम लैब में एक्सपेरिमेंट करवाते थे स्लिपिंग पोल्स वाला, करके दिखाते थे कि ये देखें यहाँ तक की कांस्टेंट स्पीड पे चल रही थी, इधर से मैंने लोड बढ़ाया तो स्लिपिंग पोल वाली सिचुएशन शुरू हो गई, वाइब्रेशन शुरू हो गई। तो सिंक्रोनस मशीन्स फिक्स्ड स्पीड पे काम करती हैं, यूनिफॉर्म स्पीड पर काम करती हैं, और ये काम वो बहुत अच्छा करती हैं। क्यों? क्योंकि अगर 50 न्यूटन मीटर के लिए बनी होती है तो 150 न्यूटन मीटर तक कांस्टेंट स्पीड पे ही रहती है। लेकिन इसका ये भी मतलब नहीं है कि एक सिंक्रोनस मोटर के आगे आप जहाज लगा दें तो भी वो काम करती रहेगी। तो इसलिए मैंने ये पुल आउट टॉर्क वाली बात बताई कि उनकी ये जो कांस्टेंट स्पीड है ये उनके रेटेड जिस चीज के लिए वो बनी है से लेकर पुल आउट टॉर्क तक सही है, वैलिड है। लेकिन हर चीज की एक लिमिटेशन होती है, तो जाहिर अगर पुल आउट टॉर्क से भी बढ़ा देंगे तो फिर वो अपना सिंक्रोनिज्म लूज भी करेगी और उस सिचुएशन में वो वाइब्रेट करेगी और डैमेज भी हो जाएगी। ठीक है, और इसकी रीजन भी दी जा सकती है कि ये सिंपल टू एंड फ्रो मोशन वो क्यों शुरू करेगी। लेकिन क्योंकि ऑनलाइन में मैं चल रहा हूँ, मैं ज़्यादा डिटेल में चीज़ों की नहीं जा रहा क्योंकि मुझे पता है कि फिर बच्चों के लिए भी मसला हो जाएगा। तो खैर यहाँ पर बात ये हो गई। अच्छा, अब बात ये इस चीज़ का जवाब कि ये तो चले आपने बात कर दी कि वो पुल आउट टॉर्क तक कांस्टेंट स्पीड पे रहेगी, लेकिन वो फिनोमेना क्या है कि जिसकी वजह से वो कांस्टेंट स्पीड पे रहती है। तो उस फिनोमेना को समझने के लिए इक्वेशन 4.61 इनफ काफी है। ये वाली जो इक्वेशन है ये इनफ काफी है एक्सप्लेनेशन के लिए कि व्हाई अ सिंक्रोनस मोटर रन्स एट अ कांस्टेंट स्पीड, एट अ फिक्स्ड स्पीड। ओके, अब हम चलते हैं इस चीज पे कि हमने इलेक्ट्रोडायनामोमीटर एज अ लोड कनेक्ट किया हुआ था सिंक्रोनस मोटर पर, और मैंने इलेक्ट्रोडायनामोमीटर की नॉब घुमाई और मैंने ज्यादा लोड अप्लाई कर दिया उस पर। तो जब भी किसी चीज पे ज्यादा लोड अप्लाई करते हैं उसकी स्पीड कम होती है, बिल्कुल मोमेंटेरली, 1 सेकंड के 1000वें हिस्से के लिए सिंक्रोनस मोटर की स्पीड भी कम होगी। अब देखें होगा क्या, आपने लोड बढ़ाया, स्पीड कम हो गई। जब स्पीड कम हो गई तो उसकी वजह से रोटर स्लो हो जाएगा। अब मैंने आपको बताया था कि ये जो टॉर्क बनता है ये रोटर की मैग्नेटिक फील्ड और स्टेटर की मैग्नेटिक फील्ड के दरमियान होता है। तो आप सोचें, मैंने लोड बढ़ाया, रोटर का टॉर्क सॉरी रोटर स्लो हो गया। जब रोटर स्लो हो गया तो स्टेटर की मैग्नेटिक फील्ड तो घूम रही थी, वो आगे चली गई और रोटर पीछे रह गया। तो जब रोटर पीछे रह गया और स्टेटर की मैग्नेटिक फील्ड आगे चली गई तो लामहला दोनों के दरमियान एंगल डेल्टा इंक्रीज हो गया। देखिए ना, एक बंदा पीछे रह गया, दूसरा आगे चला गया, तो दरमियान में फासला बढ़ जाएगा। बिल्कुल इसी तरह से रोटर पीछे रह गया घूमने में, स्टेटर की मैग्नेटिक फील्ड आगे चली गई, उनके दरमियान एंगल बढ़ जाएगा, जिसका मतलब डेल्टा बढ़ जाएगा। तो मोटर स्लो हुई, डेल्टा बढ़ गया, डेल्टा बढ़ गया, साइन ऑफ डेल्टा इंक्रीज हो गया, साइन ऑफ डेल्टा इंक्रीज हो गया, मोटर की शाफ्ट पे बनने वाला टॉर्क इंक्रीज हो गया। और जब मोटर की शाफ्ट पे टॉर्क इंक्रीज हो गया, इसका मतलब वो मोटर को कहेगा तेज चलो, तो मोटर दोबारा तेज हो जाएगी, और ये उतनी ही तेज होगी जितनी इसको स्लो किया गया था। न्यूटन्स थर्ड लॉ के तहत कि टू एवरी एक्शन देयर इज एन इक्वल एंड अपोजिट रिएक्शन, तो नतीजतन मोटर अपनी ओरिजिनल स्पीड पर वापस आ जाएगी। So this is the phenomena by virtue of which a synchronous motor runs at a constant speed. What happens that as we apply excessive load at the shaft of the motor by means of an electrodynamometer, the rotor of the motor gets slow. But as the rotor gets slow, it lags behind the stator's rotational magnetic field with a larger torque angle delta. Now, due to this increase in the torque angle delta, sine of delta is increased, because for sine theta, we can say if theta increases, sine of theta increases from 0 to 90 degrees. I told you earlier that synchronous machines typically operate at an angle of 15 to 20 degrees. So as uh, theta increases, sine of theta increases. So what happens that the induced torque at the shaft of the motor increases, and due to this increase in induced torque, its speed gets back to its original speed. So hence we say that the machine is acting at a fixed constant speed. और अगर आपने ऑब्जर्व किया हो लैब में, ये एक्सपेरिमेंट आपने मुझे यकीन है परफॉर्म किया है लैब में, तो जब आप लोड इंक्रीज करते हैं ना, हल्की सी हम की मैग्नेटिक हम की आवाज आती है, अब ये जो आवाज आती है इसी आवाज में ये सारे काम हो जाते हैं। लोड बढ़ भी जाता है, लोड के बढ़ने की वजह से रोटर स्लो भी हो जाता है, रोटर के स्लो होने की वजह से डेल्टा एंगल बढ़ जाता है, साइन ऑफ डेल्टा बढ़ जाता है, इस पे इंड्यूस टॉर्क बढ़ जाता है, और वो जब टॉर्क बढ़ता है मोटर अपनी ओरिजिनल स्पीड पे वापस आ जाती है। तो जो हल्की सी इन प्रैक्टिस एक मैग्नेटिक हम की आवाज आती है उसमें ये सारे काम हो जाते हैं। ठीक है जी, तो इंशाल्लाह यहाँ तक कई आज का टारगेट था। तो नेक्स्ट इंशाल्लाह जो नेक्स्ट लेक्चर है उसमें ये चैप्टर मुकम्मल हो जाएगा। वी विल स्टडी 3 डिफरेंट टाइप्स ऑफ numericals in the next lecture. One is related to the increase in load or the change in load. The other is the change in field current, and the third is related to the scheme where the synchronous motor was used as a power factor correction means. So inshallah we will cover those 3 numericals in the next lecture. So don't miss the next lecture. It's very important for your फाइनल टर्म एग्जाम्स एज वेल। सो अभी तक के पेपर इस लेक्चर में कोई चीज अगर आपको समझ ना आई हो, यू कैन आस्क। जी, तो खामोशी हमेशा से इकरार रही है, तो इसका मतलब ये है कि आपको समझ आ गया है। तो इंशाल्लाह सी यू नेक्स्ट वीक, एंड टिल देन टेक केयर एंड अल्लाह हाफिज़। असाइनमेंट्स टाइम पे सबमिट करवा दीजिएगा। और मैंने असाइनमेंट की डिटेल भी बताई थी कि जब मैंने बाइंडिंग पूछी है तो आपने फ्रॉग लेग बाइंडिंग, लैप बाइंडिंग और वेव बाइंडिंग को ब्रीफली मुख्तसरन बताना है। और जब मैंने आपसे पूछा है कम्यूटेशन, तो आपने डीसी मशीन्स में एसी को डीसी में कन्वर्ट करने का प्रोसीजर बताना है। जब मैंने आपसे मॉडल पूछा है, आप अपनी मर्जी का कोई भी एक मॉडल डीसी मशीन का बना के समझा सकते हैं। और सबसे इंपॉर्टेंट ये है कि जब मैंने स्पीड कंट्रोल पूछा है, तो आपने जो एग्जिस्टिंग टेक्निक्स हैं उनमें से किसी दो को डिटेल से, ये वो वाहिद चीज़ है जिसको मैंने कहा है डिटेल से बताना है। ठीक है जी, तो इंशाल्लाह आपसे नेक्स्ट टाइम मिलते हैं। टिल देन टेक केयर एंड अल्लाह हाफिज़।
अल्लाह हाफिज़ सर।
अल्लाह हाफिज़।